They are asking us to assume the Earth as a non-uniform density sphere, which is the sphere which has a density which is not uniform. And then on the surface of the Earth, now they are asking us to find the magnitude and direction of the acceleration due to gravity on the surface of the Earth. So, first, before going to that, let us first understand what if the Earth is considered as a sphere of uniform density. If the Earth is considered as a sphere of uniform density, then its density will be constant. At everywhere, its density will be constant. That means that the mass, the particles and the mass interior present inside the Earth is equally distributed. That is, the distribution of the matter inside the Earth is equal. Okay, the distribution is equal everywhere. So, as there is equal distribution of masses, then we can assume that the mass of the whole Earth can be concentrated at one specific point called center. So we can assume that the all masses can be concentrated at the specific point of the center of the Earth, that is at the center of the Earth, and we can assume that the total mass of the Earth is concentrated at that point, at that center, called center of mass. Okay, so now but through this we can assume that now we can consider that the Earth is also a point mass which is present, which Earth is also a point mass whose mass is concentrated on its center. So, assuming this, if they ask us to find the acceleration due to gravity on the surface of the Earth, so here there is a discussion about only on the surface of the Earth. So, I am taking any random point on the surface of the Earth. Then we know that the gravitational force between the 2 point masses can be given by Fg is equals to G capital M is a mass of the Earth which is concentrated towards the center of the Earth, that is mass of the Earth, into this is a small mass M test mass by R square. R square is here the distance between these two masses. So we know that the distance between the center and any point on the Earth can be its radius of the Earth. So here the R square becomes capital R square. So what happens over here is, as the gravitational force is directed towards the center of the mass, that is directed towards the center of the Earth, because the mass of the Earth is greater than this test mass, then gravitational force is attractive force, and the gravitational force on this mass will be directed towards the center of the mass. So as the gravitational force is directed towards the center, so the acceleration which is produced due to this gravitational force, that is acceleration due to gravity, will also be directed towards the center. Okay, is also directed towards the center. Not only at this point, if you pick up any random point on this Earth surface, then at that point also, since the gravitational force is attractive force, and the force on this at this point will be directed, that is gravitational field at this point will be directed towards the center of the Earth. Then when I calculate the acceleration due to gravity at this point, it will be also directed towards the center of the Earth. So what we conclude that the acceleration due to gravity at any point on the surface of the Earth, acceleration due to gravity at any point on the surface of the Earth is always directed towards the center. Directed towards the center. And one more thing, here we know that the acceleration due to gravity on the surface of the Earth is given by Gm by R square, where m is the mass of the Earth. So we know that this the when at every point which is located on the surface of the Earth is at the distance of capital R, and since the distance is same to the every point lying on the surface of the Earth, then G value, that is G magnitude, will also be same for every point on the surface of the Earth. So G is also constant. Okay, G magnitude is also constant at any point on the surface of the Earth. This was the case if the Earth was considered as uniform sphere of uniform density. Now let us check, if the Earth is considered as a sphere of non-uniform density, then what's happen over here? So if the Earth is considered as a sphere of non-uniform density, then the mass distribution will be unequal. That is, a matter distributed is distributed randomly, that is in unequal manner. So here there will be some regions in the inside the in the interior part of the earth where the mass will be directed, where the mass will be distributed more, and in some places the mass will be distributed very less. So such kind of distribution of the matter is called a unequal distribution of the mass, and such kind of so here we can say that the density of the earth is non-uniform. That is, it is not same everywhere. It's in this place, in this region, the density of the earth is more, and in this region, the density of the earth is less. So now when I take any random point on the earth, then as this mass m1 is, let's suppose this mass m1 is situated at the distance of r1 from this point, and the distance between these mass particles be r2, and distance between these mass particles be r3, and so on up to rn. Then when I calculate the gravitational force, when I calculate the gravitational force due to the mass m1, which is located at distance r1, and due to the mass m2, which is located at distance r2, the whatever the so when I get the gravitational force due to them, it will be in such a directions. So when I find the net gravitational force, that is net gravitational resultant gravitational force, that force whatever I will obtain, it will be directed in any random direction. Okay, the resultant gravitational force will be directed in any random direction. It's not directed towards center, since the gravitational force due to this mass distribution, the is net resultant gravitational force due to this mass distribution is directed in any random direction. Then the acceleration due to gravity, due to this gravitational force, due to this resultant gravitational force, will also be directed in any random direction. So what we conclude that g at, and not only over here at this specific point, if you consider at any point over here on the surface of the earth, you will find the same. That is, the acceleration due to gravity is also directed in any random direction. So what we conclude that g is randomly directed. It has different directions at different points on the surface. Coming to the magnitude, since we know that g on the surface is given by g is equals to gm by r square, then when I calculate the g due to the mass m1, it will be gm1 by r1 square plus gm2 by r2 square. So due to this, what happens over here is whatever the value g I will get here, it will not be equals to the value of g at other point. Suppose if I consider this point for this distribution, then what happens here is, as this mass m1, okay, as this mass m1 is situated at the distance of some distance of r1 dash, then the g obtained in that case will be g m1 by r1 dash square. So due to this there will be change in the values of g. So g values are not constant. So magnitude of the g is also not constant. Is not constant. Magnitude is not constant. So coming to options. So what they are in the question, they are asking to find this acceleration due to gravity on the surface of the earth will be focused on the center but not same everywhere. It is wrong, because we have seen that acceleration due to gravity was not focused towards the center, and its values were also not same. So option A is wrong. Coming to option B says that will have the same values everywhere but not directed towards the center. It is true that it will have its direction is different. It is not directed. G is not directed towards the center. But we have also seen that its magnitude is also different at different points. So option B is also wrong. Coming to option C says that will be said the acceleration due to gravity will be same or constant everywhere in magnitude directed towards the center. It is also wrong, because we have seen that at different points its direction is not directed towards the center. It's directed randomly in different directions, and its magnitude is also not constant. Coming to option D says that acceleration due to gravity cannot be zero at any point on the surface of the earth. Yes, it is true, because we know that if I find the net force on the earth's surface, if I find the net gravitational force on any point, suppose this point lying on the surface of the earth, then whatever the mass distribution it may be, so when I calculate the net gravitational force, the resultant gravitational force will not be equals to zero. Okay, whatever the net gravitational force I would get due to these mass particles, inside the earth, present inside, due to this matter present inside the earth, what are the gravitational force I would get? It will not be equals to zero. Okay, that is the net, there will be the some net gravitational resultant force existing. So since the net gravitational force, resultant gravitational force is not equals to zero, then our acceleration due to gravity, it cannot be equals to zero. So our option D is true.